we know that Laplace equation comes in the problem of potential theory. In some problems of potential theory, the physical conditions are such that they are identical in some planes which are parallel to a given plane. For example, let us take that given plane is z equals to 0. For this case, the potential psi is independent to the variable z. Therefore, the function del psi del z and del 2 psi del z square is identically equals to 0. Thus, the Laplace equation becomes del 2 psi del x square plus del 2 psi del y square equals to 0. So, this is the Laplace equation in 2 dimension. Thus, in module 2 of chapter 4, we are going to discuss about the solution of a 2-dimensional Laplace equation. For the discussion, we have to go to the slide show. First of all, I am going to discuss about the solution of Laplace equation in Cartesian coordinates. In Cartesian coordinates, the Laplace equation is given in equation number 1. Now, we are going to solve equation 1 using the useful technique known as method of separation of variables. In that method, we assume the function psi as product of two functions capital X and capital Y, where capital X, capital Y are functions of small x and small y respectively. So, assuming the solution in the form which is written in 2, if we substitute this expression in equation 1, equation 1 can be written in the form which is written in equation number 3. That means 1 by capital X d2x dx square is equal to minus 1 by y d2y dy square is equal to, let us say, a constant k, where k is called the separation constant. Now, if we equate 1 by x d2x dx square is equal to k, we will get an equation d2x dx square minus kx equals to 0, and equating the value of minus 1 by y d2y dy square equals to k, we will get another equation d2y dy square plus ky is equal to 0. Now, this separation constant k may take different values. So, according to the values of the separation constant k, 3 cases may arise. So, first we take the case where k is positive. So, in case 1, k is equal to some p square, where p is a real number. So, the corresponding equation becomes d2x dx square minus p square x equals to 0, and its solution is capital X equals to c1 e to the power px plus c2 e to the power minus px, and the solution of d2y dy square plus p square y equals to 0 is capital Y equals to c3 cos py plus c4 sin py. So, the solution of the original equation, that means solution of equation 1 is psi is equal to capital X into capital Y. So, that equals to c1 e to the power px plus c2 e to the power minus py into c3 cos py plus c4 sin py, where all cj's are constants for j equals to 1, 2, 3, 4. Now, come to the case when k equals to 0. When k equals to 0, the equation becomes d2x dx square equals to 0. So, its solution is C5x plus C6 and the y equation becomes in the same form d2y dy square equals to 0. So, its solution is C7y plus C8. So, psi becomes C5x plus C6 into C7y plus C8, where Cj's for j equals to 5, 6, 7, 8 are constants. So, the case left when k is a negative number. So, in case 3 we assume k equals to minus p square, which is a negative number where p is a real constant. So, for this case the solution psi becomes C9 cos px plus C10 sin px into C11 e to the power py plus C12 e to the power minus py, where Cj for j equals to 9, 10, 11, 12 are constants. Till now we have discussed about the solution of a two-dimensional Laplace equation, but we did not discuss about the boundary condition of those problems. Now we are going to discuss about the Dirichlet problem of Laplace equation. That means we have to find the solution of equation number 1 together with the boundary condition which is shown here. So, here we are assuming the boundary is a rectangle. So, the value of psi are given in the boundaries y is equal to 0, y is equal to b, x equals to 0 and x equals to a. And the boundary conditions are written here: psi at 0 y equals to psi at a y equals to psi at x b equals to 0 and psi at x 0 equals to some known function f x. Thus, this is an interior Dirichlet problem where you have to find the Laplacian solution of Laplacian equation grad square psi equals to 0 in the interior points of the rectangle 0 less than equals to x less than equals to a and 0 less than equals to y less than equals to b, subject to the boundary conditions which are written in equation 7. And we also assume that f x can be expanded in Fourier sine series. Now, if we consider this boundary condition 7, if we use the first boundary condition psi 0 y equals to 0 and psi a y equals to 0, then the solution 4 gives, we have to put x equals to 0 and x equals to a. So, it gives C1, if we put x equals to 0, we get C1 plus C2 equals to 0. If we put x equals to 0 in equation 4, we get C1 plus C2 equals to 0, and if we put x equals to a in equation 4, we get C1 e to the power pa plus C2 e to the power minus pa equals to 0. So, those two equations are written here. So, if we solve these two equations, we get the solution C1 equals to C2 equals to 0. So, the function psi becomes 0. So, this psi is a trivial solution of the Laplacian equation, but we are not interested to the trivial solution. So, to find the non-trivial solution, we have to think about the solution, other two solutions which are written in equation number 5 and equation number 6. Now, consider the solution 5. So, in that solution, if we put the condition psi 0 y equals to 0 and psi a y equals to 0, this leads to the solution again psi equals to 0. Thus, the solution 4 and 5 are not acceptable. So, the only solution remains is the solution 6. So, if we look at the solution 6, So, this is our solution 6. So, in this solution if we put the boundary condition psi 0 y equals to psi a y equals to 0, this gives C9 equals to 0 and C10 into sin Pa into C11 e to the power Py plus C12 e to the power minus Py equals to 0. Since we are looking for a non-trivial solution, C10 is not equals to 0 and the expression which is written in the bracket, this cannot be 0. So, the only option remains is sin Pa equals to 0 and we know the solution of this equation is sin Pa equals to 0 equals to sin n pi, where n is an integer. So, from this equation we get the values of P as n pi by a, where n takes the values 1, 2, 3, 4 dot dot. So, for all values of n, this is the solution of the Laplacian equation. So, since Laplace equation is a linear equation, so linear combinations of all this solution is also the solution of the Laplace equation, and this is called the superposition principle. So, using superposition principle, we can write the solution as psi equals to sum of n equals to 0 to infinity sin n pi x by a into a n e to the power n pi y by a plus b n e to the power minus n pi y by a. But we need to apply another two boundary conditions. One of them is psi x b equals to 0. So, if we use this boundary condition, we can express the constant Bn in terms of n, which is written here. Bn equals to minus an by e to the power minus n pi b by a into e to the power n pi b by a. Therefore, the expression for psi becomes psi is equal to half sum over n a n sin n pi x by a into exponential n pi into y minus b by a minus exponential of minus n pi y minus b by a, where the constant a n is equals to 2 a n exponential of n pi b by a. So, after simplification, we can write the solution in this form: psi equals to sum over n a n sin n pi x by a into sin hyperbolic n pi y minus b by a. But there is one boundary condition left which we want to satisfy. So, that boundary condition is psi x0 equals to fx. So, if we use that condition, we get fx equals to sum over n sin n pi x by a sin hyperbolic minus n pi b by a. And from this summation, you can see that the right hand side is nothing but the Fourier series expansion of the function fx in terms of the sine series. So, now if we multiply the both side of this summation with sin n pi x by a and integrate over 0 to a, we will get the coefficient using the orthogonality property of sine function n sin h minus n pi b by a equals to 2 by a integration 0 to a fx sin n pi x by a. So, from the last equation we can get the values of the unknown numbers capital A n. Thus, the required solution of the interior Dirichlet problem for the rectangle boundaries become psi equals to sum over n sin n pi x by a sin hyperbolic n pi y minus b by a, where a n equals to minus 2 divided by a sin hyperbolic n pi b by a integration over 0 to a f x sin n pi x by a dx. Now, I am going to discuss about the solution of a Neumann problem. Neumann problem means we have to solve the Laplace equation together with the boundary condition, and in the boundary condition, instead of the unknown function phi, the normal derivative of the unknown function phi psi are prescribed on the boundaries. So, the corresponding problem is written here. So, we have to solve del 2 psi del x square plus del 2 psi del y square equals to 0 at any interior point of the rectangle 0 less than equals to x less than equals to a, 0 less than equals to y less than equals to b, subject to the boundary condition del psi del x at the point 0 y equals to del psi del x, at a y equals to del psi del y at the point x 0 equals to 0, and del psi del y at the point x p equals to f x. Here we also assume that the Fourier cosine series expansion of small f x exist. So, in this case we are considering Neumann problem in a rectangle. Now, I am going to tell about the solution of that problem. We have already seen that if solution 4 and 5 are not acceptable for rectangular boundaries. So, we have to take solution 6, which is given here, psi equals to C1 cos px plus C2 sin px into C3 e to the power py plus C4 e to the power minus py. Now, if we use the boundary condition del psi del x at 0 y equals to 0, then it gives that C2 equals to 0 and del psi del x at a y equals to 0 gives the equation sin p a equals to 0, and sin p a equals to 0 gives p equals to n pi by a, because sin of n pi equals to 0 for all n equals to 0, 1, 2 dot dot. And if we use the boundary condition del psi del y at x 0 equals to 0, this gives C4 equals to C3. Hence, the solution satisfying the above boundary conditions can be written as psi equals to sum over n cos n pi x by a cos hyperbolic n pi y by a Now, the only boundary condition we need to apply is del psi del y at x p equals to f x. So, satisfying this condition, we get f x equals to sum over n pi by a cos n pi x by a sin hyperbolic n pi b by a, and this is nothing but a Fourier cosine series. So, the coefficient n can be obtained using the orthogonality property of the cosine series. So, to get the constants n, we need to multiply f x with cos n pi x by a, and then we need to integrate over 0 to a. So, if we do that, we get the value of n as n equals to 2 by a divided by n pi by a into sin hyperbolic n pi b by a into integration 0 to a f x cos n pi x by a dx. Thus, the solution of the interior Neumann problem is given by psi equals to a naught plus sum n equals to 1 to infinity n cos n pi x by a sin hyperbolic n pi y by a, where a0 is arbitrary constant and n is given, which is written here. Now I am going to discuss about solution of Laplace equation in polar coordinate system. The Laplace equation in polar coordinate system, which we have derived in module 1 of this chapter, is written in equation number 11. Here we are using the same techniques, the method of separation of variables. So, psi is written as product of two functions capital R and theta, which are functions of smaller and small theta respectively. So, substituting this expression for psi in 11, we can separate the equations for capital R and capital theta, which is written in equation number 12. Now, let k is the separation constant. So, the equations for capital R becomes r squared d2 capital R dr squared plus smaller dr minus p square capital R equals to 0. And if you see this equation, this is an ordinary differential equation and it is given in Cauchy-Euler form. So, with some transformation, that means if we substitute r is equal to e to the power u, so in terms of the independent variable u, that equation can be transformed into an ordinary differential equation with constant coefficients, and that can be solved exactly, and from that solution we can obtain the value of r as r equals to C1 r to the power p plus C2 r to the power minus p, and the equation for theta is d2 theta d theta square plus p square theta equals to 0, and we can find its solution easily as theta is equal to combination of sine function and cosine function, which is written here. So, the solution psi becomes C1 r to the power p plus C2 r to the power minus p into C3 cos p theta plus C4 sin p theta. So, in case 1 we have taken k as a positive constant. Now, for the second case we are assuming k as 0. So, in similar way we can prove that the expression for capital R is C5 log r plus C6 and theta is C7 theta plus C8, and psi, consequently psi becomes C5 log r plus C6 into C7 theta plus C8. Now, for the case when k is less than 0, the solution becomes, which is written in equation number 15. So, for polar coordinates, the solutions can be written in 3 different forms, which are written in equation number 13, equation number 14 and equation number 15, and all these expressions, the Cj's j equals to 1 to 12 are constants. Now, we are taking a boundary value problem, specifically interior Dirichlet problem for a circle. The interior Dirichlet problem for a circle is defined as follows. We have to find the value of the single valued function which is continuous. That function is psi, and which satisfies the Laplace equation, and on the circular region, that means on r equals to a, psi satisfies some boundary condition, which is written here psi a theta equals to f theta for 0 less than equals to theta less than equals to 2 pi, and f theta is a continuous function of theta. Since psi is a single valued function, it will satisfy the periodicity condition, that means psi r theta plus 2 pi must be equals to psi r theta for 0 less than equals to theta less than equals to 2 pi. Now, we note that r equals to 0 is a point of the domain of definition of the problem, and we know that logger is undefined at r equals to 0. So, if you see the solution in polar coordinates can be written in 3 different forms. We have already derived that. So, if you look at those forms, so if you look at the form which is written in equation 14, this solution is undefined at r equals to 0. So, solution which is written in equation number 14 is not acceptable, and if we look at the solution which is written in equation 15, here is also the solution is undefined at r equals to 0. So, the solution 14 and 15 are not acceptable. So, the only solution we can think about which is written in equation number 13. So, starting from the solution which is written in equation number 13, we need to apply the boundary condition and the periodicity condition. So, if we apply the periodicity condition in equation 16, it gives C3 cos p theta equals to C4 sin plus C4 sin p theta is equal to C3 cos p 2 pi plus theta plus C4 sin p 2 pi plus theta. So, after simplification, we get the values of p is equals to n, where n is 0, 1, 2, 3, that means all positive integer values and 0. Now, using the principle of superposition, the solution psi can be written as sum over n Cn r to the power n plus Dn r to the power minus n into n cos m theta plus Bn sin n theta. Again you can see that psi r theta is finite at r equals to 0. So, it is possible only when Dn equals to 0. So, substituting Dn equals to 0 and defining the constants in this way which is written here, we get, or we can write down the equation in the form, the solution in the form psi equals to half a0 plus sum over n r to the power n n cos n theta plus Bn sin n theta. Now, we are applying the boundary condition which says that psi at r equals to a, theta equals to f theta. So, satisfying this condition, we get f theta equals to half a 0 plus sum of n equals to 0 to infinity a n a to the power n into a n cos n theta plus b n sin n theta. So, from this expression it is clear that this is the Fourier series expansion of the function f theta. So, the coefficients a n b n can be obtained using the Fourier transformation like which is written here. So, if we multiply that equation f theta with cos n theta and use the orthogonality property of the function cos n theta and sin n theta, we get the expression for a n b n which are written here. Thus, psi can be written as 1 by pi integration 0 to pi f theta into half of plus sum n equals to 1 to infinity r by a to the power n cos n theta minus phi d phi. Now, it is to be noted that there is an infinite series in the summation and we want to find the sum of the value of this sum. To find the value of this sum, we assume C as this sum of r by a to the power n cos of n phi minus theta, and S is assumed as the sin r by a to the power n into sin n phi minus theta. Now, if we calculate C plus Is, then we get a GP series, and the common ratio of this GP series is less than 1, since mod of r by a is less than 1 and mod of e to the power I phi minus theta is also less than 1. So, the sum of the GP series can be written in this form, r divided by 1 minus r. So, this is written here. Now, if we equate the real part and imaginary part from the both sides, we can get the expressions for C and S. Since we are interested to find the value of C, we equate the real part from the right hand side and we get the value of C, which is written here. Therefore, the solution psi becomes 1 by 2 pi integration over 0 to 2 pi a square minus r square f phi by a square minus 2 a r cos phi minus theta plus r square d phi, where r is less than a. This integral is known as Poisson integral formula, and this gives a unique solution of the interior Dirichlet problem for a circle. Now, I am going to discuss exterior Dirichlet problem for a circle. The exterior Dirichlet problem for a circle is defined as follows. We have to find the value of the function, single valued function psi, which is also continuous at any point exterior of a circle r is equal to a, which satisfies the Laplace equation, which is written in equation number 11 for r greater equals to a, 0 less than equals to theta less than equals to 2 pi, and it will psi will satisfy the boundary condition psi a theta equals to f theta, where f theta is continuous function of theta and psi is bounded as r going to infinity. Now, there is a difference between an interior Dirichlet problem and an exterior Dirichlet problem. In case of exterior Dirichlet problem, we have to drop the term r to the power n because that term is not bounded as r going to infinity. So, the solution is of the form which is written in equation number 20, and in the solution you can see that the term r to the power minus n is present because this term is bounded as r going to infinity. Now, if we use the boundary condition psi a theta equals to f theta, we get f theta equals to half a 0 plus sum n equals to 1 to infinity a to the power minus n a n cos n theta plus b n sin n theta, and using the Fourier series we can obtain the values of a n v n which are written here. Thus, the solution of exterior Dirichlet problem becomes psi equals to, which is given here. Then proceeding exactly as we have done in the earlier case, in case of interior Dirichlet problem, we can obtain the value of the infinite series, and we finally subsequently we can get the expression for psi, which is written here, psi equals to 1 by 2 pi integration 0 to 2 pi r square minus a square f phi by r square minus 2 a r cos phi minus theta plus a square d phi for r greater than a, and this is our required solution. Now, I am going to discuss interior Neumann problem for a circle. So, for this case we have to find the continuous function psi which satisfies the Laplace equation together with the boundary condition where the normal derivative of the function psi is prescribed. So, we have to solve the Laplace equation 11 together with the boundary condition del psi del n equals to, for this case it is del psi del r equals to g theta, where g theta is some continuous function of theta. Since phi must be bounded at r equals to 0, we take the solution in this form where r to the power minus n term is missing and we have to consider only r to the power n term. So, solution is written here, and so this solution can be written in the form which is written in equation number 21, where the constants a0, an, bn are defined in this way. Now, we want to satisfy the boundary condition which says that del psi del r equals to g theta. So, using that condition we get g theta equals to sum over n a to the power n minus 1 into an cos n theta plus bn sin n theta. It is again a Fourier series expansion of g theta. So, using the theory of Fourier series, we can obtain the values of an and bn, which is written here. Therefore, solution becomes psi equals to half a plus integration 0 to 2 pi g phi into the infinite sum of r by a to the power n, a by n pi to cos n phi minus theta d phi. Again we can find the value of this infinite sum using the procedure which we have done in the earlier cases, assuming C as this sum and S as this sum, and then computing C plus IS, we can find the value of the infinite sum, then equating the real part of the previous expression from both sides, we get the expression for C which is written here. The psi equals to half a minus a by 2 pi integration 0 to 2 pi log of 1 minus 2 r by a cos phi minus theta plus r square minus a square g phi d phi, where r is less than a. Now, I am going to discuss about the Laplace equation in spherical polar coordinates, where the independent variables are r, theta and phi. In some cases, there is some axial symmetry in the problem. So, for that case, there is a symmetry about the polar axis theta equals to 0 and psi is independent of phi. So, the Laplace equation in spherical polar coordinate becomes, which is written in equation number 23. Again we are using the method of separation of variables to find solution of this equation. So, we assume psi as product of function r and theta, where r theta are function of smaller and small theta respectively, and the surface theta is called the zonal surface harmonic. So, if you substitute 24 into 23, we get the equation. We can separate the expression for capital R and capital theta, which is written in 25. Let k is the separation constant, and we are substituting the value of k as n into n plus 1. So, if you substitute that, we get the R equation for capital R, which is written in equation number 26, and equation for capital theta, which is written in equation number 27. Equation number 26 is an ordinary differential equation which is in Cauchy-Euler form. So, its solution can be obtained easily. Now, if we look at equation number 27, we need to substitute mu equals to cos theta. Now, the equation taking mu as independent variable, equation 27 reduces to the form which is written here d d mu of 1 minus mu square d theta d mu plus n into n plus 1 into theta equals to 0. This is famous Legendre equation, and we know the solution of Legendre equation is Legendre function or Legendre polynomials. So, the solution is written in equation number 29. So, this is linear combination of Legendre functions of first kind and second kind. Thus, the solution can be written using the superposition principle. Psi is equal to sum over n, an r to the power n plus bn r to the power n plus 1 into Cn Pn mu plus Dn Qn mu. Thus, in module 2 of chapter 4, we have discussed about the solution of a two-dimensional Laplace equation using the method of separation of variables. We have discussed the cases taking different coordinate systems like Cartesian coordinate system, polar coordinate system and spherical polar coordinate system. We have also shown that how the solution changes with the boundary conditions. Thus, we end this module.